All right, so what we're going to do in this lecture is look at actually deriving what our shear stress distribution is for a beam subjected to transverse loads. And so we're going to look at, for a given section, what our shear stress distribution is. And so remember from our previous video, what we did is we looked at sort of an intuitive feel of what the that distribution would be, and we found out that we know that at the top and the bottom of the section has to be 0, and right at the neutral axis we're going to have our maximum shear stress. So with this video, we're going to put some numbers to that and try to prove it. So again, we have our simply supported beam laid out here, point load in the middle, shear force and bending moment diagram. And the way that we're going to derive this is we're going to look at a small section of this beam. So we'll just essentially cut it out there, and that section will have length dx. And so if we follow this down, well, onto our bending moment diagram, on one side, we will have the moment M applied there, and then at the other side we will have it's going to have the value M plus a little delta M, and so that makes sense. A shear is going to be a change in bending moment with respect to distance. And so if we draw the free body diagram of this little block, what we end up with, so here's our rectangle here. And it has, a moment on one side. It has a moment M plus delta M. On the other side, it's got length dx, and it's got a shear V1 on one side and V2 on the other. And so what we want to do is, just find what our shear stress is along the height. And all we're going to do, so we already know what our bending moment distribution is. That's just going to be, because we're assuming plane sections remain planed, we'll just have a linear distribution of bending stress. And like what we saw in the last video, well, we know that we need a longitudinal shear to resist bending stress at a given height. So we can use that and some equilibrium, and then we can work out, well, what is that distribution? So let's draw this in 3 dimensions to maybe this will illustrate this a little bit better. So let's draw in 3 dimensions and just draw the stress state on there. So we have our free body diagram of the forces. If this is our stress state, we'll draw this block, and we'll essentially be looking up at it. So it's got some length here, and that length, again, dx. Height, it's got a width b, and that's just going to come back to what our section geometry is here. So that's our block. Now let's just look at what our stress is on here. So on the one side where we have M, well, we know that we have a stress distribution and this is going to be our neutral axis here. So we have this linear stress distribution coming along, and that is going to have the value sigma x, and it will obviously be in compression at the top, tension at the bottom. And then, and if this is our neutral axis, bring it across. On the other side, for M dm, the bending stress there is just going to be ever so slightly bigger and again, compression on the top, and tension on the bottom. And that value is just going to be sigma x plus this small change in bending moment. And that small change in stress really equates to delta sigma over dx times dx. And that's just, by definition, that's just that extra little bit of stress which is located there. All right, so that's our bending stress. If we want to find what our shear stress at a point is, well, we can take into account where if we cut off the top here, we're going to reveal the longitudinal shear stresses. And because where we have two surfaces meeting, our longitudinal and our transverse shear stress need to be the same. That's essentially the tactic we're going to use to determine what these transverse shear stress distribution is. So if we just take the top of this here, we'll just shade that in, make it clearer. And then let's just draw it over here and then just draw the stresses which show up on it. So, we've got, again, just sort of looking down from below. So we know that, cutting here at the top, we have some that same bending stress. In compression. And on the other side, again, slightly larger bending stress due to the small delta M. So that's the bending stress, but then also here on this surface that we've cut and removed, we have some shear stress tau. And again, we've got width B here, and we'll call this dimension here on this face, so shade that in, we'll call that dimension A prime for that area that this is acting over. So this is kind of our three-dimensional representation of what's going on. Let's just redraw it quickly in 2D, just looking in at this face here, just to make it a little bit easier for us to set up our equilibrium equations. The 3D is nice to just get your head wrapped around what the behavior is, but it can be a little bit confusing when setting up the equilibrium. So again, just sort of redrawing this face and then this face here just to see what the stress state is looking like. So again, here's our block. dx wide, and then we'll just draw the stress state. I'll draw it in red just for clarity. Compression on the top, tension on the bottom, and that has a value of sigma. And then on the other side, slightly larger, again, going through the middle there for 0. And that's going to be sigma plus delta sigma over dx times dx. And then if we look at just this little area up here, we know that sitting right at that surface is a shear stress, tau. And so we can kind of think of this as a few different forces. You have sort of a, F over here, On the other side, you have a F plus a little dF, so a tiny additional force. And then our tau really is what that, dF equals. And that's just going to be tau times b, the width, times dx that's acting over. And then if we just look at the cross-section, just to kind of complete the picture here before we set up our equations of motion. So if that's our neutral axis there, we have this little area. That area is A prime. And we'll say that the distance to the centroid of that area, we'll call that y1. And so that will become apparent here in a moment. So this is our, that's our free body diagram. That's our stress state. Now, in order to derive what our shear stress is and really try to find, if we can find this shear stress, well, then we can find the shear stress right at the corner there and there. And we can do that going down the depth. So to do that, let's set up our equilibrium equations. So let's sum the forces and the x and let that equal 0. And remember that, to get a force out of a stress, we need the stress over an area. So we'll start on this side. So again, our free body diagram is pretty much just coming off right up here. We're going to have sigma times little delta A. So we'll look at that integral over that. So this is over this entire area. We're just integrating this volume of stress to get that. Plus, well, then we have our shear stress. So that's going to be shear stress tau times the width of the section B times the length. So this is our area, so that's dx. And then it's going to be minus this area, this stress integrated over this area. So it's going to be minus sigma plus delta sigma over dx dA, and we'll take the integral of that over A. And all of that has to equal 0. So again, just kind of recap, this is essentially force 1 plus dF, the shear force, and F plus dF. And for those to cancel out, well, the two F's are the same, so that means that our shear force is going to be whatever small change in stress relates from that moment across there. So I think we should just go ahead and expand this out. Sigma dA prime plus tau b dx. We'll just split this out into two integrals. So we can multiply out the dA. And it's a polynomial, so we can just take those integrals separately. So we're going to have A prime sigma dA prime minus A prime delta sigma over dx times dx dA prime equals 0. So this force and this force, those cancel each other out because we have a positive and a minus. This is a minus, we'll move that over to the other side. So we get tau times b times dx equals A prime delta sigma over dx dA prime. All right, so that's an interesting little equation, and it kind of just shows what we had up here. If this is F plus dF, well, the two forces cancel each other out, and so whatever little change in force has to come from that shear. And that's just all this equation falls out. So, in order to, oh, sorry, I'm missing a dx over here. Well, let's continue. This is not a terribly useful form of this equation yet, so let's continue this. So this is a dx. That's a constant. That's just the length of the block. So because it's a constant, we can move it out. So we get tau times b times dx equals dx a prime over delta theta dx dA prime. So these two cancel out. And so now we're left with shear stress times the width of the section equals integral of delta sigma over dx dA prime. And let's just call that equation 1 for right now. So we're almost in a form which is useful for us. So we have this integral of this derivative of stress, and so, well, you know, can we make this a more useful form for us? Well, for example, if you know, our typical bending stress is my over I, well then d theta is just going to be dm y over I, because the distance which we're going up is just a variable on our cross section. That's just, you know, wherever we're trying to find the shear stress, and I is going to stay constant. So that means we can substitute. We'll call this 2. So we'll just sub in equation 2 and equation 1. And that gives us tau times the width equals a prime delta m over delta x y I dA. Now here's another interesting one. So delta m, so our change in moment with respect to change in our x distance is just the definition of shear. I mean, that's really what our shear force diagram is coming out. This is why the slope of the so the value of the shear force diagram is the slope of the bending moment diagram, because this is the derivative. It's simply the derivative of this. And so, yeah, that's all. The only way we can create a shear is to have a change in moment over the length. And so, well, that means that, you know, kind of by definition, delta m over delta x equals v. It just equals our shear at that point. And so, you know, that's by definition. And we'll call that equation 3. So let's sub in equation 3, and what do we find? So we get tau times b equals a prime v y1 over I dA. Well, v and I for a given section are constant, so we can move those outside the integral. Equals v over I times a prime y1 dA. So this section here should look really familiar. So this is just our definition of the first moment area. Which is kind of cool. So that means that we can this is a common section property which we can calculate in sort of an engineering term. So we almost have a useful equation. So if we work out this integral and then we divide out the b, we get tau equals v over ib a1 y bar, where y bar, so that's A1, that's this area here, so the area above the section of interest, and then it's just the distance from the centroid there to our center. And we call, so that's A1 is the area above section of interest, and y bar is the distance from the centroid of A1, so of this here, to the neutral axis. And because this is used so often, to simplify this formula, we just give the letter Q equals A1 y bar. And so often you'll find the shear stress is written VQ over IB. And that's it. That's our derivation for shear stress in the section at any height. So, any height above the neutral axis, that's how we can get it there. So that concludes the derivation. What we'll look at next is applying this across some sections, and we will see how the shear demands vary over there and sort of what those profiles look like. So with that, that's the end of this lesson.